All right, here we go. So we're finishing out section 1.1. Now we have one-to-one functions. So a one-to-one function is a function. So pause right there. This is saying to continue this, we have to first satisfy being a function. So for each input, it will only go to one output. And then it says in which each output value corresponds to exactly one input value. So function means the input only goes to one output. One-to-one means the output only goes to one input. So that way, there's a one-to-one correspondence between inputs and outputs. Nobody's cheating on anyone. Now, you can have something that is one-to-one and not a function. But typically, we are starting with a graph, and when we ask, is it one-to-one, we're wanting to know, is the inverse of it going to be a function? All right, so vertical line test is our graphical way to test, is the graph representing a function? So remember, a function is for each input, there is only one output. So when we draw that vertical line through a graph, so here, let's sketch our graph. There we go. This graph is a function. Why is it a function? So some people call this the pencil test. You know, if I move my pencil across the graph, anywhere I stop it, it only hits the graph in one point. Yes. Why does that work? What is this vertical line representing? So this can take a little twist in your brain to think of it this way, but instead of just as a vertical line, think of it like a placeholder highlighting all of, when we think about vertical lines, remember these are stacks of points that share an x coordinate. So a vertical line is just a placeholder for a bunch of points that share one x value. So the vertical line is really just saying, for this x value, what's going on? So anywhere I pause my vertical line, so I can pause it here, 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 it's a placeholder for the x value that it's contacting on the x-axis, but then we see on the graph, it's only hitting in one spot. So that's x value, one spot on the graph is one y value. Now it's okay if the y values repeat, like between points, as long as we're not getting two different y values somewhere. So this is one y value, one y value, one y value. So when a graph passes, anywhere I pause my vertical line, my pencil, if it only hits the graph once, that means the graph is a function. What does failing look like? So if a graph is not a function, let's go orange, then the graph has to have a place where there's more than one y value for one particular x value. So let's kind of sketch in here. There is our x value. So even if the left side, it's only on the left one side, only on the right the other, all it takes is one spot for there to be two y values for us to say not a function. Okay, now horizontal line test. The horizontal line test is testing if something is one-to-one. It does not test for functions. You have to do the vertical line test first to see if it's a function. Once it's a function, we'll often ask, is it one-to-one? does it pass the horizontal line test? So think about what we just went over with the vertical line test. That vertical line was a placeholder for an x value. So when we do the horizontal line test now, a horizontal line is a collection of all the points that share a y coordinate. So a horizontal line is a placeholder for a y value. So what I'm checking for, it's just like the vertical line test, everything we're checking for, it's just what we're using and what it means. If it only hits the graph once with a horizontal line, then it is 1-to-1. 1-to-1 means that the inverse of this graph will be a function. Failing would be like our pink graph here. If I drop a horizontal line on it, I've got, wah, come on. There. 2 x values for 1 y value. Not 1-to-1. So writing out O-N-E, T-O-O-N-E takes forever. So mathematicians tend to go 1-1. And we just read it 1-to-1. Don't write 121 because that looks like the number 121 instead of 1-to-1. So even though this one is not 1-to-1, it is a function. So if something is a function and it's 1-to-1, then it's going to pass the vertical line test and the horizontal line test. So what this means is this graph, if it is passing both the vertical and horizontal line test, the graph only goes in one direction. It either only goes up or it only goes down. Because if it turns around anywhere, once we go back down, like if we started going up, once we turn around back down, now we've doubled up horizontally. So we're not 1-to-1 anymore. So just interesting side note. Or it can all go down. All right. So the only other thing left in section 1.1 is to talk about the toolkit functions. So these are functions that you should be familiar with already, particularly if you took 1073 or college algebra. The only ones not on the list currently are exponential and logarithms. We're going to cover those at the end of the semester, but we're going to focus more on the properties and the algebraicness of it. So you should be familiar with those graphs, but I didn't put them on this list. It's okay if they're there, though they're on the bigger list. All right, so the constant function, f of x equals c. This is also often written y equals c. Y equals horizontal line. This is a function. The vertical line is not on here because the vertical line is not a function. It is the definitive non-function because x is trying to go to every y value in existence. Super cheating code. But y equals c, every x value is going to the same y value, but they're each only going to one spot. The identity function, what we put in is what we get out. So f of x equals x or y equals x. Absolute value, written with those straight bar or the pipe symbols, and that is whatever we put in, we get the value back out, but we always get a positive. So if we put in a positive, we get what we put in, but if we put in a negative number, we're going to get a positive back out. Oh, I did not mean to do that. There. All right, then we have our quadratic. Very normal, makes a U, cubic, the reciprocal and reciprocal squared functions. Boy. So the reciprocal and reciprocal squared functions. Come on. You can do it, Graph. I believe in you. It's being weird because I copy pasted it from somewhere. Okay. So there is our reciprocal function. There's that vertical asymptote and there's horizontal asymptote. Reciprocal squared function. The right side of the graph is the same kind of shape, although it will more quickly hug each of the axes. So 1 still maps to 1, but 2, instead of mapping to a half, maps to a fourth. 3 is going to map to a ninth. So it's going to get even closer to the x-axis even faster than 1 over x. But on the left side, it's going to mirror the right side. It's going to be super fast, but it's all positive outputs. So this is where you get behavior that's going in the same direction on either side of an asymptote versus opposite directions on either side of an asymptote. Just one of the ways in the formula to see what the graph should do there. We are not going to mess with these too much, but you should be familiar with them, especially for calculus. You should be able to visualize, all right, if I'm dividing by x minus 2, that means there's a vertical asymptote at x equals 2. If I'm dividing by x plus 3 squared, that means there's a vertical asymptote at x equals -3, and the graph goes in the same direction on either side. So knowing which way the graph goes will be important in calculus because we talk about the limits at asymptotes and it's all infinity behavior, but is it positive or negative will be the question. All right, got that one there, and then we'll come back for 1.2 once I fix my screen.